Hello friends, welcome to my lecture on power series. An important special case of a series of complex valued functions is the general power series. Sigma n equal to 0 to infinity Cn z minus z naught to the power n, which can be expressed as C naught plus C1 z minus z naught plus C2 z minus z naught to the power square and so on, Cn z minus z naught to the power n and so on, where C naught, C1, C2, Cn's are in general complex numbers and are called the coefficients of the power series. Z naught is any fixed point in the complex plane called the center of the power series. A special case of this equation 1 is the power series where z naught is equal to 0, that is sigma n equal to 0 to infinity Cn z to the power n equal to C naught plus C1 z plus C2 z square and so on. So, the center of this power series is at the origin. Any complex polynomial say f z equal to C naught plus C1 z plus C2 z square and so on, Cn z to the power n can be thought of as a power series which converges for all z. So, here you can say that Cn plus 1, Cn plus 2, the coefficients Cn plus 1, Cn plus 2 and so on are all zeros. So, it represents a power series and it converges for all z, because for any z in the complex plane we can find the sum of the series. Now, the power series sigma n equal to 0 to infinity z to the power n converges for all z in mod z less than 1 and is equal to 1 over 1 minus z on this circular disc mod z less than 1. If z equal to 1, then we will have the nth term of the power series as 1, and so the nth term of the power series does not go to 0 and therefore, the series does not converge. So, we can see that the series converges for all z in mod z less than 1. Let us take the nth partial sum of this series Sn equal to 1 plus z plus z square and so on z to the power n minus 1. Then it is a geometric series and therefore, Sn is equal to 1 into 1 minus z to the power n divided by 1 minus z. Now, if mod of z is less than 1, then limit n tends to infinity z to the power n goes to 0, okay. It is equal to 0 and hence limit n tends to infinity Sn z is equal to 1 over 1 minus z. So, the sum of the series is 1 over 1 minus z whenever mod z is less than 1. Okay. So, we can say that the series converges for all z such that mod of z is less than 1 and is equal to 1 over 1 minus z on this circular disc mod z less than 1 with center at z equal to 0 and radius 1. If z is equal to 1, then we can see that here also we can see Sn is equal to 1 plus 1 and so on 1, that is n. Okay. So, limit n tends to infinity Sn is equal to infinity and therefore, the series diverges for z equal to 1. Hence, the series converges for all z such that mod of z is less than 1 and diverges at z equal to 1. Now, let us consider the power series sigma n equal to 0 to infinity z to the power n over n factorial. Then we can see that this series converges absolutely for all finite z. We can do that by ratio test. So, apply. So, here f n z, the nth term of the series f n z is equal to z to the power n minus 1 upon n minus 1 factorial. Nth term of the series f n z is we are writing this series as sigma n equal to 0 to infinity f n z. So, f n, this is nth term of the series. We start with n equal to 0. So, nth term, this is nth term, actually this is nth term. Okay. So, nth term is actually here, it is f n minus 1. f n minus 1 is the nth term of this series. So, f n minus 1 z is z to the power n minus 1 over n minus 1 factorial, and then f n z is equal to z to the power n by n factorial. Hence, limit n tends to infinity, mod of f n z divided by f n minus 1 z is equal to limit n tends to infinity, z to the power n by n factorial into n minus 1 factorial divided by z to the power n minus 1. So, this is equal to limit n tends to infinity 1 over n times mod of z, okay, and this is equal to 0 for all finite z. Okay. So, the limit is less than 1, okay, and therefore, the series converges absolutely by ratio test, the series converges absolutely for all finite z. Actually, it is nothing but the exponential z, okay. This sigma n equal to 0 to infinity z to the power n by n factorial is exponential z. The given series is exponential z. Now, like in the case of real calculus, we know that every power series has a radius of convergence which lies between 0 and infinity, 0 less than or equal to r less than infinity. So, here also in the we are considering a generalization of the power series in the for complex functions. So, for every power series given by 1, let us see, given by 1, for every power series given by this equation 1, okay, there is a number r 0 less than or equal to r less than or equal to infinity called the radius of convergence, such that the series converges absolutely for every z with mod of z minus z naught less than r. If 0 is less than or equal to rho less than r, then the convergence is uniform for mod of z minus z naught less than or equal to rho. If mod of z minus z naught is greater than r, the series diverges, and for mod of z minus z naught equal to r, the series may or may not converge. The sum of the series is an analytic function in the disk mod of z minus z naught less than r. Its derivative can be found by term differentiation, and the derived series has the same radius of convergence. So, this result we have in case the limit here if the limit of mod of Cn plus 1 over Cn exists, okay, then it is equal to 1 by r. You can also find this radius of convergence r by using the ratio test. So, 1 by r equal to limit n tends to infinity mod of Cn raised to the power 1 by n. If this limit does not exist, then the Cauchy-Hadamard formula says that 1 over r is equal to limit superior n tends to infinity mod of Cn raised to the power 1 by n. Now, the assertion A, that is the power series converges absolutely for every z with mod of z minus z naught less than r, can be easily seen by applying the ratio test to the series 1. Okay. We shall show that the series converges uniformly whenever mod of z minus z naught is less than or equal to rho, and rho is strictly less than r. So, let us first show this. The circle mod of z minus z naught equal to r is called the circle of convergence of the series in equation 1. So, when mod of z minus z naught is less than or equal to rho and rho is less than r, we shall show that the power series converges uniformly. Now, why it converges uniformly? The power series converges uniformly for if rho is less than rho dash less than r. So, let us take a number rho dash which lies between rho and r. Let rho be less than rho dash and rho dash is less than r. Then the nth term of the power series mod of Cn z minus z naught to the power n is less than or equal to mod of Cn mod of z minus z naught is less than or equal to rho. So, rho to the power n, and this is less than or equal to rho by r to the power n, because but since 1 by r is equal to limit n tends to infinity mod of Cn to the power 1 by n. Okay. So, since this is 1 by r is equal to limit n tends to infinity mod of Cn to the power 1 by n, there exists some n naught such that for n greater than or equal to n naught, mod of Cn is less than or equal to 1 by r to the power n. So, mod of Cn is less than or equal to rho by r to the power n, and rho dash is less than r, rho dash is less than r. So, 1 by rho dash is greater than 1 by r we can say 1 by r is less than 1 by rho dash. So, this is less than rho dash, rho by rho dash to the power n for sufficiently large n, okay, for n greater than or equal to n naught. From here we are getting this inequality. So, in view of limit n tends to infinity mod of Cn to the power 1 by n equal to r, we get this inequality. Now, since rho by rho dash is less than 1, the geometric series sigma n equal to 1 to infinity rho by rho dash to the power n. Okay. This is convergent, and hence by Weierstrass-M test the series in 1 is uniformly convergent. Okay. So, this series converges uniformly in mod of z minus z naught less than or equal to rho less than r. Since every term of the series in 1 is analytic, we can see that every term of the power series sigma Cn z minus z naught to the power n is analytic. So, the sum function of the series is analytic in mod of z minus z naught less than or equal to rho, and rho less than r. Further, the derivative of the sum function can be obtained by term by term differentiation. Hence, if fz is equal to sigma n equal to 0 to infinity Cn z minus z naught to the power n and mod of z minus z naught less than or equal to rho less than r, then f dash z will be equal to sigma n equal to 1 to infinity n Cn z minus z naught to the power n minus 1, and here you can see the coefficient of z minus z naught to the power n minus 1 is n Cn. So, limit n tends to infinity n Cn raised to the power mod of n Cn raised to the power 1 by n is equal to limit n tends to infinity n to the power 1 by n into limit n tends to infinity mod of Cn to the power 1 by n. Now, n to the power 1 by n as n goes to infinity is equal to 1, so 1 into 1 by r. Okay. So, you can see that the coefficient of z minus z naught to the power n minus 1 is n Cn, and when we take the limit of mod of n Cn to the power 1 by n, we get 1 by r. So, this means that the radius of convergence of the derived series is also r. Okay. And this follows from the fact that limit n tends to infinity n to the power 1 by n equal to 1. So, radius of convergence of the derived series is also r. Now, let us consider an example, say sigma n equal to 1 to infinity n to the power n z to the power n. So, this series can be expanded as z plus 2 square z square 3 cube z cube and so on, and here we can see that Cn is equal to n to the power n. So, mod of Cn raised to the power 1 by n limit n tends to infinity is equal to limit n tends to infinity n to the power n whole to the power 1 by n. So, limit n tends to infinity n which is equal to infinity, and this is equal to 1 by r. Okay. So, this implies 1 by r is equal to infinity, and so r is equal to 0. So, radius of convergence of this series is r equal to 0. That means that this series converges only at the point z equal to 0 and nowhere else. Now, let us consider another example, sigma n equal to 1 to infinity z to the power n by n square. Here we can see here Cn is equal to 1 by n square. Okay. So, limit, so 1 by r equal to limit n tends to infinity mod of Cn to the power 1 by n is equal to limit n tends to infinity 1 by n square raised to the power 1 by n. We can write it as limit n tends to infinity 1 by n to the power 1 by n whole square. Okay. Now, we know that n to the power 1 by n goes to 1 as n goes to infinity. So, this is equal to 1, since limit n tends to infinity n to the power 1 by n equal to 1. Okay. So, what do we get? R is equal to 1, Hence, the radius of convergence of this power series is equal to 1. And now let us see, when you take consider the series of absolute terms. Now consider sigma n equal to 1 to infinity mod of z to the power n by n square. So, this is sigma n equal to 1 to infinity mod of z to the power n divided by n square. Now, if you take mod z equal to 1, so if mod z equal to 1, what we get, the series sigma 1 by n square, okay, which is known to be convergent series. Okay. So, convergent, it is a convergent series, and therefore, the given series converges absolutely for mod z less than or equal to 1. For mod z less than or less than 1, it converges because its radius of convergence is r equal to 1. Okay. So, the given series converges absolutely for mod z less than or equal to 1. Now, let us consider the derived series. The derived series is sigma n equal to 1 to infinity n z to the power n minus 1 divided by n square, which is sigma n equal to 1 to infinity z to the power n minus 1 divided by n. Now, here again if you take the coefficient Cn, okay, the coefficient Cn is the coefficient of z to the power n. The coefficient of z to the power n is one over n plus 1. Okay. So, limit n tends to infinity mod of Cn raised to the power 1 by n is equal to limit n tends to infinity 1 over n plus 1 raised to the power 1 by n. Okay. And if you find this limit, it is limit n tends to infinity 1 over n to the power 1 by n 1 plus 1 by n to the power 1 by n. Okay. So, when n goes to infinity, this goes to 1. Okay. When this goes to infinity, it goes to 1 because n to the power 1 by n goes to 1, and 1 plus 1 by n goes 1 plus 1 by n to the power 1 by n also goes to 1. So, this is 1, and therefore, r is equal to 1 because this is 1 by r equal to this. Okay. So, r is equal to 1, okay, and therefore, the series derived series, okay, also converges for mod of z less than 1. It converges absolutely for mod of z less than 1, but if you take z equal to 1, what do we get? At z equal to 1, the derived series becomes sigma n equal to 1 to infinity 1 by n, okay, which is a divergent series. So, the derived series, okay, converges absolutely for mod of z less than 1. Now, let us consider the case where the limit of mod of Cn to the power 1 by n as n goes to infinity does not exist. Okay. So, there we use the Cauchy-Harder formula. The radius of convergence of the power series sigma n equal to 0 to infinity Cn z minus z naught to the power n is r equal to 1 over limit superior n goes to infinity mod of Cn to the power 1 by n. So, let us see how we prove this. So, let us assume that r is equal to 1 over limit superior n tends to infinity mod of Cn to the power 1 by n. We shall show that r is the radius of convergence of the power series sigma Cn and z minus z naught to the power n. Now, since mod of Cn to the power 1 by n is greater than or equal to 0, limit superior will always be greater than or equal to 0. So, if it is infinity, 1 over infinity will become 0. So, this r will belong to this limit superior n tends to infinity of a sequence of non-negative real numbers will always be non-negative. So, r will always be non-negative, and moreover if this limit is infinite, it 1 over infinity will become 0. So, this r will belong to this semi-closed interval 0 infinity. It is r is always greater than or equal to 0. Now, first we discuss the case when r is less than infinity. So, if r is less than infinity, let us choose any r greater than r. Okay, let us take, if r is less than infinity, let us take any r greater than r, then limit superior mod of Cn, limit superior n tends to infinity mod of Cn to the power 1 by n will be greater than 1 by r. Okay, limit superior n tends to infinity mod of Cn to the power 1 by n is equal to 1 by capital R, but 1 by capital R is greater than 1 by r. Okay. So, mod of Cn to the power 1 by n into r is greater than 1 for infinitely many indices, and r we can say mod of Cn into r to the power n is greater than 1 for infinitely many indices n. Hence, Cn z minus z naught to the power n does not approach 0. This is nth term of the series. Okay, nth term of the power series does not approach 0 for any z with mod of z minus z naught equal to r greater than r, because if the series is convergent, then the nth term must go to 0. Here what is happening is mod of Cn r to the power n is greater than 1 for infinitely many indices n. Therefore, Cn mod of z minus z naught to the power n, okay, does not approach 0 for any z with mod of z minus z naught equal to r, where r is greater than r. So, the power series diverges for any z with mod of z minus z naught greater than capital R. If r is greater than 0, choose 0 less than r less than capital R. Okay. Then if r is strictly greater than 0, then choose 0 less than r less than capital R, then limit superior n tends to infinity mod of Cn to the power 1 by n is less than 1 by r. Okay. So, this follows from this is limit superior n tends to infinity mod of Cn to the power 1 by n is equal to 1 by capital R, but 1 by capital R is less than 1 by r. Okay. So, if so and so mod of Cn into r to the power n is less than 1. From here it follows that mod of Cn into r to the power n is less than 1 for all but finitely many indices n, and hence for any z with mod of z minus z naught less than r, we have sigma n equal to 0 to infinity mod of Cn z mod of z minus z naught to the power n is equal to sigma n equal to 0 to infinity mod of Cn into r to the power n mod of z minus z naught over r to the power n, which is less than or equal to m times, because mod of Cn into r to the power n is less than 1 for all but finitely many indices n. So, we can say that mod of Cn into r to the power n can be made less than or equal to m for all indices n. So, this is less than or equal to m, sigma n equal to 0 to infinity mod of z minus z naught over r to the power n, which is less than infinity, because mod of z minus z naught is over mod of z minus z naught is less than r. Okay, mod of z minus z naught is less than r. Okay, so so this is a convergent series, and therefore this is less than infinity. Thus, the power series converges for any z with mod of z minus z naught less than r, and hence it follows that the radius of convergence of the power series is r. The sum function of a power series is said to be represented by the power series within its circle of convergence. This raises the question whether a function can be represented by two different power series with the same circle of convergence. Now, the following theorem answers this question. So, if sigma n equal to 0 to infinity Cn z minus z naught to the power n and sigma n equal to 0 to infinity dn z minus z naught to the power n are both convergent series for mod of z minus z naught less than r, where r is greater than 0, and have the same sum for every z in the circle of convergence, then the two series are identical. So, if there are two power series which are both convergent in the same region of convergence and have the same sum for every z in that in the circle of convergence, then the two series must be identical, that is Cn is equal to Dn for all n. This is called the identity theorem for power series. Now, so here what is happening is that this series and this series both have the same sum, therefore, C naught plus C1 z minus z naught plus C2 z minus z naught whole square is equal to D naught plus D1 z minus z naught, D2 z minus z naught whole square and so on, and they converge both in the region mod of z minus z naught less than r. Now, since the sum function of both the series is since they have the same sum, okay, and some function is analytic in the region mod of z minus z naught less than r, and therefore, the sum function is continuous for every z in mod of z minus z naught less than r, and therefore, if the sum of this series is say f z, okay, say f z is equal to sigma n equal to 0 to infinity C n z minus z naught to the power n, then f z is analytic in mod of z minus z naught less than r, okay, and f z is analytic means f z is continuous, okay. So, continuity of f z implies that limit z tends to z naught, f z is equal to f z naught. So, when z tends to z naught, okay, when z tends to z naught, f z must be equal to f z naught, and f z naught is equal to here C naught. Okay. If this is g z, if this is g z, then limit z tends to z d. So, again by the same argument, g z is analytic in the region mod of z minus z naught less than r. So, limit z tends to z naught, g z is equal to g z naught, okay. So, when z tends to z naught, okay, the left hand side tends to C naught, the right hand side tends to D naught, and so C naught must be equal to D naught, okay, by the continuity of the sum function. Now, let us assume that C n is equal to D n. We are going to prove that C naught is equal to D naught, C 1 is equal to D 1, C 2 equal to D 2 and so on. So, let us assume that C n is equal to D n for n is equal to 1, 2, 3 and so on up to m. Then we shall show that C n is equal to D n for n equal to m plus 1 also. So, then by omitting, so when C naught is equal to D naught, C 1 equal to D 1, C n T 2, C 2 equal to D 2 and C m equal to D m, okay, then we can omit the m terms from both the sides. So, by omitting the first m plus 1 terms on both sides of this equation 2, what we will have? We will have C m plus 1 z minus z naught to the power m plus 1 plus C m plus 2 z minus z naught to the power m plus 2 and so on equal to d m plus 1 z minus z naught to the power m plus 1 plus d m plus 2 z minus z naught to the power m plus 2 and so on, okay. So, by omitting the first m plus 1 terms on both the sides, the series reduces to this equation, and then we can divide by z minus z naught to the power m plus 1. So, when we divide by z minus z naught to the power m plus 1, what we will get? We will get C m plus 1 plus C m plus 2 z minus z naught, okay, C m plus 1 plus C m plus 2 z minus z naught, C m plus 3 z minus z naught whole square and so on equal to d m plus 1 plus d m plus 2 z minus z naught, d m plus 2 3 d m plus 3 z minus z naught whole square and so on, okay. So, we obtained this one, okay, this series. Now, both these series represent a function which is continuous at z equal to z naught, because when we remove the terms, still this series represents analytic function, this series represents analytic function, this also represents analytic function. So, they are continuous functions at z equal to z naught, and therefore, Cm plus 1 must be equal to dm plus 1. At z tends to z naught, this will tend to Cm plus 1, and z tends to z naught, this will tend to dm plus 1, and they are continuous. So, at z equal to z naught, they must be equal to Cm plus 1 and dm plus 1. So, this is Cm plus 1 and this is dm plus 1. So, Cm plus 1 must be equal to dm plus 1, and therefore, by mathematical induction the theorem is proved. Now, two power series may be multiplied term by term or rearranged in any desired order throughout the region lying in the interior of any common region of convergence, because both the series are absolutely convergent in the common region of convergence. With this, I would like to end my lecture. Thank you very much for your attention.